Okay, it's 11:30, so let's get started. Welcome everyone. Nice to meet you again. It's been more than a year since the last Ignite, so I couldn't be more happy about being back here. Let's see if this works. So, for those who have no idea who I am, my name is Sami Laiho. I'm from Finland. Teach around the world. I currently travel 200 days a year. All around the world, teaching anything related to operating system internals, troubleshooting, or security. Last years, I've been in TechEd and Ignite. I've mainly been teaching about troubleshooting, but this year it seems that it's mainly security. It seems to be a hot topic. So I got 4 sessions, 1 today, 2 tomorrow, and 1 on Thursday. If you need to schedule something, schedule the one which is Thursday afternoon. No, sorry, Wednesday afternoon. Do-it-yourself penetration testing Windows OS. It's in the big A1 room, so there should be quite a lot of room there. But for me, the story goes that I've been prepping 2 sessions for the whole year, basically. And then I had 2 75-minute sessions, but then I was supposed to have 2 20-minute theater sessions, which I basically didn't have any slides because it was like going to be 20 minutes and takes me a while to do some demos, and I wouldn't need any slides. So, but then they changed both of these theater sessions to be 45-minute breakout sessions, which was of course super fun for me. I love it. It's a lot easier than standing at the expo with the 15 seats they allocated. So I honestly had no idea someone has reserved seats. It's so cool. Awesome. just saw that sign, reserved seats. Nice. So, this is my 4th year in US for Ignite, or it was TechEd before. I always start my sessions with some lessons on our nice language from Finland and our culture. So I will do this once again. People will tell me all the time at the speaker room that it's like, what the hell are you talking about? Like, that's no one can understand the language that I'm speaking. And I still dare to say that it's quite simple. So I took an example here. We have an English word here, which is actually freaking horribly hard because there's how many words? Nuclear power plant, steam, condensation, compressors, gearbox. So that takes 8 words to say same thing as in Finland, we only need 1. So ydinreaktori, generaattori, lauhduttaja, turbiini, ratasvaihde is a lot simpler than using crazy amount of words to say the same thing. I also get the other thing which people will tell me is that you Finnish people, you don't do anything else but you just drink all the time and you got the highest suicide numbers in the world and stuff like that. So I thought I'd share some statistics with you which might perhaps explain a little bit why this might be so. So if you think about the northern parts of Finland, this is from a local newspaper currently. So it says the times when the sun goes up, okay? So in Helsinki it goes up at 8:47, and in the middle part of Finland it goes up at 9:34, and in the northern part of Finland it goes up on the 16th of January 2016. So there are reasons, all right? This was just so pure fun I had to do this. So I traveled 200 days. For some reason, my wife said that I don't deserve to have an office at the home, okay? So I had to give up my office and have to minimize my workspace, which is now in our bedroom. And so I took all the papers I had out. So I'm going to go PDF only. Why the hell would we need that old piece of paper? So let's get rid of it. So I took all the certificates that I had and decided I'm going to scan those as well. Because I had when I was a kid, I used to print out business cards which would say, I'm MCSE, MCSE plus I, MCSE 2000, MCSE plus messaging, MCT, MCP, and whatever, okay? So I was so proud of those. And at some point I stopped it. And now I thought, should I actually list my certificates? And then I put them on the floor. I scanned them and I was like, how the hell am I going to put this on a business card? So I have a way. And so now I did this. So I actually weighed them down. So I have 2.6 pounds of certificates. I'm not going to anymore have them on the business cards. I'm just going to announce how much my certificates weigh, okay? Little bit of housekeeping. On my 75-minute breakout sessions, I'll exchange some business cards for swag. So if you want to swag, there's those 2 sessions that I had since the beginning. So that's Wednesday afternoon and Thursday afternoon. The first year I came to TechEd, I had these T-shirts with the Finnish word for administrator. Then we had caps, I think the next year. Then we had beanies. And now we've got bumper stickers, okay? So very easier for me to bring them. Someone asked me and said, you have to bring 500. I can't come from Finland and bring 500 like hoodies or whatever. So I had to come up with something else. The bad thing was the TSA stopped me instantly because I had those in my backpack and they look like a huge pile of dollars or bills. So they're stacked up. It's like, what the hell have you got here? Stickers. Yeah, sure, what does that mean? It's administrator in Finnish. No way. Yes, it is. How cool is that? Let me through, okay? Anyway, what are we here for? We're here for Secure Kernel. I've heard so many sessions during this time already saying that Secure Kernel is like a virtual machine. I would totally dare to disagree on that, even on the keynotes, talking about this minor virtual machine. Well, you could in a way think it's kind of a virtual machine, but I would first always think about the fact that if your computer has a secondary kernel running it called Secure Kernel, does it have memory? Because if you would have a virtual machine, that would mean that you would have dedicated memory to a virtual machine, which means that if I have 16 gigs of memory, I would give some part of that memory to that other virtual machine. But I don't. All memory is shared, okay? So that is like the first indication that we're not talking about a traditional virtual machine, all right? So what I'm trying to aim with this session is talk a little bit about how the secure kernel actually works. So not just the concepts, what you've seen, hope probably more than enough during the keynotes. We're going to talk about how that actually works behind the scenes, okay? So first of all, if we talk about user mode and kernel mode, those are actually rings, which are CPU technology. CPU needs to know if a certain piece of code running on the CPU can access some part of memory or not, and it has rings. Those rings are actually numbered in a bit weird way, so kernel mode is ring 0 and user mode is ring 3. What happened to 1 and 2? Did they get lost in translation or whatever? Actually, the thing is that back when NT was introduced in 1993, Intel and AMD CPUs already supported 4 rings. And they could have done this with like kernel mode, semi-kernel mode, user mode, isolated user mode. Easily with the CPU technology only, that would have been just totally doable. But NT had to support other CPUs as well. So there were CPUs, Alpha, for example, that didn't support more than 2 rings on the CPU. So they had to take the least amount that would be supported by the most amount that would be supported by all of the CPUs. That's why we end up with this weird numbering of ring 0 and ring 3. Every modern CPU nowadays supports more. It's kind of funny because if we would start again, don't believe anything you hear for the next 2 minutes, okay? How many times have you heard Microsoft guys saying, Windows 10 is the last Windows ever? Quite a lot, I'd say, okay? I start hearing it in totally different ways now. I used to hear it like, okay, so they're just going to keep upgrading Windows 10. I also teach so much operating systems that people will ask me like, so what's the deal? All 64-bit code goes into System 32, and all 32-bit code goes into SysWob 64. So, like, why don't they fix it? It's been like that forever, and why don't they fix it? Well, they can't really fix it without breaking the compatibility. So what I hear all the time is actually like, Windows 10 is the last Windows ever. Have you ever heard them saying Windows 10 is the last operating system by Microsoft ever? I don't. I haven't. That's what I hear now all the time. I'm waiting for, like, I don't know what they're going to call it. Doors. Or whatever. As I said, don't believe anything you heard during the last 2 minutes. It's totally my personal opinions, okay? They're going to get sued, by the way, if they choose doors. Okay, so anyway, I think if you would build a new operating system now, you see it with Edge, okay? So they have the old Internet Explorer, which will be there probably forever. They can't fix it, so they build a new one. That's why I think at some point they have to like just prove to us that they can build a working, oh sorry. Oops. Rewind. Try that again. Okay, so they're going to build an operating system that doesn't have these minor faults in it. Okay. So that would be doable. Now we have to do it in a bit different way. So first of all, what happened to 1 and 2? We did that. What are -1 and -2? So -1 got introduced later on. We had already these rings, and these are only like concepts about rings. That's not an official CPU ring, but they're called -1 and -2. So -1 is the hypervisor, because it was built later on and then put below the kernel, which means it goes like below 0, so they call it -1. From security perspective, these are really important because the lower level you hack, you always own the upper levels. So if you hack the hypervisor, you own both kernel and secure kernel. What's -2? Who knows? Silicon. What? Silicon. Who said UEFI? That's the closest one, I'd say. It's called SMM, System Management Mode. It was introduced back in 386. You get a prize. I have security vests with the Finnish word for järjestelmävalve. There you go. In Finland, they're called security vests, but Mark Minassi says that in US, those are worn by prisoners. But I don't know, inmate, järjestelmävalvoja, whatever. Okay, so that's SMM, -2, okay? Now, the traditional way how the OS works, we got a kernel mode and we got a user mode. Anything that's running in kernel mode owns everything running in the user mode. So if you can put anything into the kernel mode, you own the whole box, okay? How many of you have yourself, with your own bare hands, extended the Windows kernel? 1. 2. I'm going to get a lot more when I rephrase the question. How many of you has ever installed a device driver? Okay. Kernel is easy to extend. There are APIs to extend the kernel by building a device driver. So anyone who can build a device driver, install it in the system, owns the box. That's as simple as that. Think about pass the hash, what they're talking about in the traditional way. Kernel mode is running there, and then you put user mode process called LSASS. LSASS. And LSASS has the hashes that you need to pass to another computer. Pass the hash is a fundamental function of Windows NT to allow remote administration. It has to be there for Windows to work like it works. It's just now used for bad purposes. So pass the hash is a normal concept of the operating system. Pass the hash attacks are the bad ones that they use it for their benefit, for bad purposes. So if LSASS is running in user mode, it means that anything running in the kernel can access those hashes, which means that you just install a device driver and you can do pass the hash, or you use Mimikatz, which actually uses a debug privilege, which allows you to access the user mode. Anything running in the kernel mode owns everything running in the user mode. That's the traditional way. Now, what happens in Windows 10 for the first time is that we introduce another kernel next to it, okay? Your kernel, NTOS kernel, it's just an executable and a few drivers and some code running in the operating system, okay? It's running there, but then we get another one. It's a secure kernel next to it. It's sitting on top of the hypervisor. This won't work without the hypervisor. except in the future release of Doors version 1.0 probably. But as long as we stick with Windows, we need a hypervisor to do this. What we're going to do is we're actually going to have a kernel and a user mode on top of it, and then next to that kernel we got a secure kernel, and then we have what's known as isolated user mode running on top of that secure kernel. What we're aiming at is this, okay? Oops. As long as you have anything in the kernel, it cannot access the isolated user mode. We transform and move that LSAS onto the other side, to the isolated user mode, preventing anyone from the normal kernel from accessing those hashes. That's what credential guard is, okay? Let's go into specifics how this can be done, because this is kind of against all the rules of the operating system, that this would be that the kernel couldn't access some piece of memory, because it owns the box. But let's talk about that in a while. Isolated user mode, it has a lot of names, but people are talking about secure kernel all the time, but actually like the isolated user mode, it's actually what they kind of refer to as being a virtual machine or a sandbox or whatever. If you introduce the new thing they announced yesterday with Edge, Barcelona, whatever, the new, it's got a cool name, and I have it on the slides because I changed the slides yesterday because of that. It would add like one kernel more. So some people asked me yesterday, now they are putting Edge in the isolated user mode. No, Edge is not, that's not what they're doing. That's a bit different technique. So it is not just what are known as trustlets like credential guard. It's a bit different, but we can get back to that in a while. So now what we have to do is we have to somehow make sure that no normal thing running in the kernel can access that isolated user mode. What about things running in the secure kernel? Well, there's the biggest fundamental difference. There are no APIs. You cannot extend the secure kernel. Only Microsoft can extend the secure kernel. That's the most important difference in the whole thing. Because otherwise we would just install a secure driver and do the same thing again. You actually can't do it. Creating a secure driver in the first place. Hard to do. So, technically what happens is that the hypervisor below these modes actually works with a new thing that it assigns, and it associates what's known as a VTL with every virtual processor that's running. And these VTLs give like another way of saying how trustworthy something is. We had the rings, which go like up and down, and then we have these VTLs, which go lateral, so that we can have a kernel next to a secure kernel, next to a super secure kernel, or whatever in the future, or the new Edge thing, okay? These are, Microsoft learns from their mistakes, or the CPU companies, manufacturers learn from their mistakes. So what they started up was, they started with this normal world being VTL 0, and then you go to secure world, which is VTL 1, and now we can add later on. So we don't have to come up with -1, -2, -78, okay? It's just a weird, bit silly way of doing it in the old way. So now this works a bit better. So the hypervisor actually associates these VTLs that will give us the possibility to control three things. What we can control is we can prevent someone from reading anything in a certain place in the memory, which is basically what credential guard is. We can prevent someone from executing something in a certain place in the memory, which is effectively what device guard is. And then we can also control writing so that we can actually communicate between these two kernels. So we can do, what we can basically at the end of the day do is say that this certain bit in the memory has rules. And they're different for these kernels. The other one can read it, the other one can write it, okay? It's like Finnish police officers. Bad Finnish joke. Anyway, so isolated user mode. Let's go, actually, we can go one forward. I just mentioned this already. So what is that secure kernel thing? If you would like to see it on the disk, if you would like to somehow feel that it really exists and it's not just a concept, there actually is a normal secure kernel.exe. That's your kernel, like NTOS kernel.exe. That's your secure kernel. It's very tiny. You can see the size difference there is 300K compared to about 8 megs. So it's a tiny, tiny kernel compared to the real kernel. But if that secure kernel needs to do everything that the other kernel does, then it would mean we would have 8 megs and 8 megs. We would effectively double the size of Windows from kernel's perspective. That's why it's not a real kernel. You could say that it's more of a proxy kernel, okay? So it proxies certain things from that secure kernel to the traditional kernel that will actually do something. Let's say you want to write something to the page file, for example. There's no reason for us to duplicate the code that allows us to page things on the disk, because the kernel can do it already. So what we instead do is we use a proxy kernel which will ask the normal kernel to do this. This comes with problems. What if you have secret stuff on the secure kernel, like you normally do? What if you would, from the secure world, ask Windows to write a page of memory into the page file, going through the normal kernel? Problem would be that the normal kernel could read it. To prevent someone from reading something, we encrypt, okay? But what if I ask the operating system, the normal kernel, that please encrypt this before you put it in the page file? It could still read it. Which means crypto code, for example, is in the secure kernel as well. So all crypto code can be done on the secure kernel so that it can encrypt everything before giving it to the normal kernel to write it to the page file. So some code needs to be in the secure kernel as well. But the minimal amount so that we don't consume memory more than needed. If you want to put something in the kernel mode, it needs to be signed with a certain signature from Microsoft. It's not just signed by Microsoft, it actually is signed by a certain kind of certificate. It says isolated user mode there, which means that if you would like to cheat this system, you would have to steal that certificate, sign it and put it, then you could run anything you wanted in the secure kernel basically. But it's protected by this certain certificate, okay? They can communicate with each other and also from secure kernel to normal kernel, there's two mechanisms. So they used what same as Azure calls blobs. So there's one way of transferring data. So you can just transfer some information from the secure side to the normal side, or if you have to, sorry, I'm mixing this up. So storage blobs is inside of processes running in the secure mode, and mailboxes are between the two modes. So there are two mechanisms for moving information. So everything goes through what's known as a marshal. When I teach in the US, I have a problem, which is when I get paid, my customer will give me a check. And if I go to Finland and give a bank a check, they're going to ask me, what is that? Because we don't use them. It costs me 15% of the value of the check to cash it in, and it takes 2 weeks if I do it in Finland. So I have to do it in US always. So I got my check, and then I go to a place. And if you think about the place where you go to cash a check, like a bank, you watch through this plexiglass. And there's that small tray that you use to move stuff below that plexiglass. That's kind of what the marshal is. It's the best way to think about it. I basically have access to all the resources. I see them through the plexiglass, but the only way to communicate through something is put it through that tray and have that marshal there to see if it's appropriate or not. If something will be attacked in this thing, it's that marshal. If you would ask me what's the best place to somehow get this compromised, it's that. So, because there is code that has a list of check these things out before giving it forward, okay? So that list must be of interest to all hackers, because there is a list. So that might be attacked in the future. Now, all of this still is against all the rules of the operating system. Because, by definition of Windows, kernel has access to all memory pages. Every single one. If you think about Windows, it's built by the assumption that the kernel mode memory is shared by everyone in the kernel, and it should be able to read it. That's why they had to go to the hypervisor guys. Help us out building this secure kernel by giving us a mechanism of fooling the operating system below the kernel on how we can actually access memory or not. If you think about a normal process running in Windows, it uses a concept of virtual memory. Virtual memory is an abstraction layer between the physical RAM and your applications. Why do you need virtual memory? Well, think about this. An application developer would start their lives. If we didn't have virtual memory, they would basically start by starting an executable, starting a process, and they would go through the memory to see if there's some empty spaces in the memory that I could use. Instead, everyone starts at the same 0 address, and then we have the virtual memory manager who takes care that those are mapped into certain places in the physical memory, or maybe in some cases they're actually paged out to disk. That's an old way, and that's sometimes also referred to as first-level address translation. So, this happens on another level as well. Difference for the previous slide. Now on the left-hand side you have a virtual machine 1. On the right-hand side, you have virtual machine 2. They need to do translation as well, because the virtual machine believes that it's looking at physical RAM. But we know it's not, because it's the virtual RAM that it sees. So if the previous one was first-level address translation, what is this? SLAT. Good. Second-level address translation. No prizes for that, sorry. We only had 4 inmates in Finland, so I have it's a very, very secure country, so I only have 4 vests with me, 1 per session, okay? So, second level address translation. That's the thing that happens below the VM, which means that we have to tell the VM that this is your real memory, although it's not real. So we have these tables here, page table that says guest physical address and system physical address, GPA and SPA. We do the same kind of thing. The good thing with this is the magic in the whole thing. The good thing is that we also have an access mask. With SLAT, we can say that this memory will be given to that VM, but it's read-only. Okay? Why do we want to have a CPU with SLAT? Because then the CPU takes care of this address translation. If you don't have SLAT, it needs to be done by Windows kernel itself. Hypervisor, meaning you have to have 1 meg more memory per VM, because you have to store these page tables. But if the SLAT is on the CPU, then you can outsource that from your operating system to the CPU. So this one is called SLAT, okay? Now, what we do here is we actually introduce 2 SLATs. So we have a kernel mode and a secure kernel mode, and then we have SLATs. But we have 2 different ones. Like this. Now we can have on the left-hand side, now see it's not the VM anymore. Kernel, right-hand side you got the secure kernel. We have a SLAT for both of these, meaning that we can say that if the normal kernel asks for a certain memory address, it has no restrictions. If the secure kernel accesses something, it can if the normal kernel reads something, it can't even read anything, so it's totally forbidden from it. And then we got the secure kernel that can now read and execute from a certain place. You shouldn't have read, write, execute to a memory address. That's one of the oldest tricks in the book of getting malware in your machine. Then you have a place that can be executed but also changed at the same time. So that's usually not the case. So what is this VSM really? I wouldn't say it's a VM, but it's kind of a functionality that's possible due to virtualization technology. So hypervisor allows us to do this, but it's not a VM. There was still someone yesterday on the expo doing a theater session saying that there's this small VM. It's not a VM. Whoa. What's happening? Okay, so what are we running inside of the secure mode now? There's that isolated user mode, and it runs what's known as trustlets. So if you hear trustlet term, it means a process running in the isolated user mode, which is running on top of the secure kernel. Secure processes running in that isolated space. We got different trustlets. So those trustlets currently are 4 of them. The last one was introduced with 1607 release just a few months ago. So what we have there is credential guard, which is LSA-ISO.exe. Then we have biometrics information, bio-ISO.exe, which is the new one. That 1607 release introduced the 4th trustlet. Then we have virtual TPMs if you're running Server 2016. Super important. If you're a server admin more than a workstation admin, this is of huge importance to you. How does virtual TPM work? Well, TPMs are built by this consortium. Well, the specifications are built by a consortium called TCG. And TCG says that a TPM needs to be a place that we can say that the kernel cannot access. That's why you had this physical chip before, and now it's part of your firmware if it's a TPM 2.0. But anyway, it's a place which is hidden even from your kernel. So that's why we couldn't have virtual TPMs with server before. Because if you put something virtual in RAM, that would mean that anyone can read it in the kernel. So TCG would not allow Microsoft to build virtual TPMs because they can't meet the specifications. They can't say that we put the TPM in memory and the kernel can't access it. Now you can. Just hide it there. Put the TPMs there and your kernel can't access it. Now we have virtual TPMs, which allows shielded VMs and all sorts of crazy cool stuff for Server 2016. BitLocker encryption on VMs. Having VMs that hypervisor administrator cannot actually access, which is very cool for all sorts of scenarios. And then we've got the kernel mode code integrity, which is the one part of what's known as device guard. Think about AppLocker. My main income from consulting comes from taking away people's admin rights. Tomorrow I'm going to present 45 minutes of demo about why the hell you cannot be an admin. Now, I still go to places where my customers will tell me, well, we are actually looking at it this way. We have admins, but we use AppLocker to restrict what they do. The AppLocker doesn't work for admins at all. It's the craziest thing ever. AppLocker is not meant to deal with admins. Even the documentation says it only works for limited users. Administrators can bypass it because it's in your normal Windows. You own the box, you got a driver, you can run whatever you want. AppLocker can't do anything for you. Okay? Now, device guard, totally different thing. With device guard, we can actually build a rule set saying that if this piece of code is not on the whitelist, that slat will not give it execute rights. It's a physical way of preventing things from running. That's awesome. More is coming. Edge Barcelona. What's the name? Windows Defender Application Card. WDAG. Don't know. WDAG. Don't know what I'm going to call it. Anyway, I just learned it yesterday, like you. So that's more of thinking like creating another container next to this what we already have. It's more of having a third kernel running stuff on top of it. It's not a trustlet. That's what people asked me yesterday. Is that a trustlet? Technically not. It's not a trustlet. It's a sandboxed environment to run stuff, but it's not a trustlet. So it's not running in the isolated user mode. It's running in another one. You can't keep this thing secure unless you have 3 things in your hardware. I know I'm being a bit picky here, but if you really honestly want to make it secure, you need to have this. First of all, you need to have your secure boot on so that we can verify that no one broke the trust of you having a working UEFI which is not compromised. So your bootloader and your UEFI, we will need to have secure boot on. Otherwise, we can go below ring. We can actually go to below the ring 0, which means if we get to the level -2, we own anything running in the hypervisor, which means we run any kernel running on top of it, which means we own everything, okay? DMA, tough one. I'm going to do a DMA, direct memory access attack against BitLocker on actually tomorrow afternoon. And Microsoft still insists that it doesn't work for Windows 10. Let's see. I've given them 2 weeks to do stuff so that I wouldn't demo what I'm going to demo tomorrow. Anyway, what we need is an IO-MMU. What's that? Input-Output Memory Management Unit. IO-MMU. We got an MMU which has taken care of memory management. It's been in a Windows for a in a CPU for a long time. IO-MMU does the same thing for IO devices. IO-MMU can put rule sets saying those DMA devices cannot access this part of the memory. An IO-MMU is not known as an IO-MMU, it's known as VTD for Intel, or AMD-VI for AMD. So you can't look for IO-MMU if you buy a computer. It's VTD or AMD-VI, okay? That IO-MMU needs to be there so that we can block direct memory access. Think Thunderbolt 3, the best example currently. Thunderbolt 3 has direct memory access to all of your memory. So if we allow that, there's no use of having a secure kernel because any DMA device can read the secure kernel. So it totally kind of takes away the benefit that we're trying to gain. Okay? That's why you need an IO-MMU. And then you need to have a TPM so that we can store secrets, because the secure kernel needs a place to create, verify certificates and stuff like that. So 3 things you need to have to keep this secure. I think I have those terms here. Yes, I do. So Intel VTD, AMD VI, because some people ask me all the time that what kind of computers should they buy. IO-MMU, now don't get too excited because someone hears this like I would be saying, IO-MMU, like in a Mac, it actually would prevent you from gaining access to your hard disk encryption keys. Currently, Mac leads this field. They actually, the newest Mac devices with the newest OS X, they actually can prevent DMA attack against hard disk encryption. IO-MMU makes Windows have ability to block DMA. And so many people will come to me like, yes, we got an IO-MMU, so you will not attack our BitLocker anymore. Now they forget one important thing, which is that the BitLocker information is not stored in the secure kernel. I hope they move it there as fast as possible. But the BitLocker code is in the normal kernel, so you can access that as whatever you like. Okay? It's not. They would have the technique, but the location for that BitLocker information is still the old one. So it's not in the protected world. So that's what I hope they will fix soon. How do you enable secure kernel? You need SLAT, secure boot TPM, and IO-MMU. Before the newest release, the anniversary release of Windows 10, you had to enable BCD store to support it. Now you don't. You will just enable that feature from the add remove features list. You actually only have Hyper-V there nowadays. You had a feature called isolated user mode. If you now go to that place, it doesn't exist anymore. Because now if you enable Hyper-V, which is a requirement, it will automatically be enabled. You don't have to do it anymore. They removed one step. And now we have a few minutes left, so let's see this in action. Now we need to change machine. I'm going to do a simple demo, I'd say. Many people will always show me demos on how to do pasta hash with Mimikatz or Windows Credential Editor or whatever. I will not do that, because you can see those during this week like more than enough. What I'm going to show you is a very simple demonstration on why the hell this will not work at all when you have secure kernel, okay? So let's just do a simple process dump. I need admin rights. Now I have a new laptop, so I can still use my fingers. Those of you who don't know, I can't use admin rights, so I have a limited user and an admin user. So let's start that as an admin. Somehow I'm always afraid of giving you the finger. It's like, always afraid they're going to throw me out of the conference. But we have a code of conducting. Let's just quickly change this. I actually forgot to change these. Here we go. Let's do a process dump from sysinternals. Proc dump, and I'm going to dump LSASS, okay? 0.3 seconds, you got the content of LSASS, okay? Which has all the hashes. Now take Mimikatz, give it that dump, you do pass the hash. I have a driver. I'm an admin, I can install a driver, what process dump does, and that's why we can do it, okay? Now, try to do the same for LSA ISO. That's the isolated one running in secure kernel. How would you know you have that running in secure kernel? You could go and run Task Manager, and you can see two things here. First of all, what you see is something here known as secure system. That's your indication that you're running the secure kernel. There used to be a process called system, now there's another one called secure system, okay? And then we've got LSA ISO running here as well. So LSA ISO is here. That is the secure part of your local security authority. Only domain user accounts go there. So only domain user accounts benefit from this, not local ones. So let's try this. Proc dump LSA ISO, invalid access to memory location. That's a hardware error. Simply, the whole kernel, the whole operating system has no access to that memory. That's like having a main switch below the computer on your RAM modules saying that this one is off for you. That's what it looks like as an error message. It's like a physical error of not being able to access the memory. All right, let's switch back. Want to learn more? What I have left is a few more sessions. I hope you'll come to those sessions as well. You can send me email whenever you want. I have a disclaimer. The disclaimer is, you send me email, I will answer. It doesn't cost you anything, and as long as you're willing to accept the answer of I don't know. If you still after that insist that I should know, then I start charging. Find me on Twitter, please. At Sami Laiho. I got a blog-free newsletter. I got a lot of courses running online. I'm a Pluralsight author as well. Have two cool sessions there. I hope you remember to do the evals. That's what we live for, and that's what makes us come back every year, hopefully. So please do fill in the evals. And with that, I will thank you.